Okay, brilliant. So should we take a picture at the end? Brilliant. Well, thank you very much, everyone, for coming to this presentation. So every year, we ask a group of students that are selected by Valentina, which is an architect that used to work in RISE, that now works at UCL. And actually, she moves now. I don't think it's working in UCL anymore. But I asked her to select the projects from our student that could be more relevant for the work that you're doing in RISE in Lesotho. So our students have the task to design a house for a family of four in Lesotho in two locations, in Maseru and Mokhotlong. And those two locations were selected initially just because it's the location where we have weather data. Okay, that is the only reason. And they have to design this house for a family of four, but the house has some requirements. It works like a childminder for 10 kids during the weekdays, and during the weekend when it operates as a house. And one of the other requirements of the house is that it needs to be completely passive and comfortable, healthy, and hopefully use some of the materials, and if not all the materials that Rice at some point was interested in. There are five that we found in your website, and I think Valentina at some point was looking at those materials. So I'm going to pass it to you, Daniela, so you can say a few words, because I mean, the whole idea of this project at UCL is that the student face a problem that actually you're facing on a daily basis and actually has some interest. And what we hope is that some of the ideas that the student have proposed at some point can be implemented in Lesotho. Probably one of the students that are here in present would like to go to Lesotho at some point, work with you guys and help you. That will be amazing if that happens. Um, it's also an opportunity for me as an academic to learn from you, from what RISE is doing, but also from the experience of all our students. We receive a student from many countries in the world, all with different backgrounds, architects, engineers, mathematicians, well, I don't know what kind of the professional we have this year. What I can see here in the room is also we have Valentina, which is the architect that used to work in RISE, and we have Phil Simmons, which is the program director of the master that we have and where these students have taken. So I'm going to pass it to you, Daniela, so you can say shortly what RISE is. So what is this project for you and what it means for you, for RISE?
Super. Thanks a lot, Hector, and thanks everybody for having worked on this. As some of you may already know, we are a not-for-profit social enterprise, and we're trying to basically address two key challenges that we have in Lesotho and also in other sub-African countries, which is one, the problem of youth unemployment. And by upskilling young people through a fellowship program called In Loco, and a number of our fellows who've been through that program are on this call now. And the other is to improve the quality of design and construction. In Lesotho, we've got a very unique climate, as you all will have learned, right? Everybody assumes Africa is hot all the time, but that is not the case. We have massive temperature changes, as low as -10 in winter, and then in the daytime it goes up to 16 degrees in winter time, and then in summer it gets as high as 30 degrees. And yet there's still a massive lack of affordable housing, and also we've got a problem of a lot of imported materials. Over 70% of the building materials are imported. So we're always looking of ways in using locally sourced, low carbon materials that can be produced or adapted in Lesotho so that it contributes towards job creation as well as the local economy. And also to try and promote passive design, which is something that is still not sort of a standard. A lot of houses now, you know, as you will have learnt, the traditional vernacular, yes, built with a lot with adobe and thatch roofing, but now a lot of the urban housing to save money and time and are built from concrete blocks and single corrugated metal sheets, which are an oven in the summer and freezing in the winter. And we have been working on this challenge of affordable housing for several years now. We've run an international design competition, and we want to find this solution to take it both to the Lesotho Housing Department, which is a parastatal, as well as to private development companies, which might end up actually being a faster route because with the amount Lesotho is a great democracy, which means we have a lot of changeover of governments, but that also means lack of continuity of policy. So there's a downside to that. So there's been quite a lot of delays in getting the land secured, and the buy-in from the parastatal to invest, because at the moment they've got very poor designs, they subcontract, they don't do master planning, and also there's problems because people still want to grow their own vegetables and have their own food gardens, and they're okay with living next to each other but not on top of each other as we look at densification of housing in urban areas. So the work that you've done, we hope that some of them will be able to take it into practice. We will be fundraising, and that's why also the British High Commissioner will be joining us as well, because obviously you being UCL, there's the British interest, but she can also assist with advocating and lobbying with government for funding for these projects. We've also had two very interesting conversations, one with UN Habitat, who are very interested in our model and taking it to other sub-Saharan African countries. And affordable housing and lack of employment opportunities are two of their key goals that they're trying to address. And more recently, with FSC, the Forest Stewardship Council, who we've just finished a project building a football stadium for a not-for-profit made of FSC timber. And they are extremely interested in taking our model to their other key partners. And they're inviting us to take the case study to a conference, the ESG conference, in October in Johannesburg, where we will have the ears of all the banks and a lot of big financial institutions. So, we need a sort of a pool of database of information, case studies, and data that you all will be have worked on. And I'm really looking forward to hearing your presentations so that as and when the land is secured and the funding is secured, we can start building some pilot testing and then take this to scale. So that hopefully gives you a little bit of background as to how it fits into the bigger landscape, not just in Lesotho, but hopefully to other sub-Saharan African countries as well.
Thank you very much, Daniela. So you guys, you see how much, I mean, probably your projects can influence what they're doing in Lesotho. So but let's go to the presentation. So just because the order in which they arrived to the meeting today, so we're going to go with group 7, then group 13, and group 4. And well, I'm going to ask you also to introduce the member of the group and probably what are your backgrounds, so because that is quite important, and then well, go to your presentations. Hello, Martin. Good
Hello,
morning.
I'm very sorry to be late. Good
Yeah,
afternoon,
good
Maseru.
afternoon. Yes, we are just starting. Well, actually,
Brilliant.
I give an introduction, and then Daniela just finished her introduction. We are going to start with the group presentation, but just
Wonderful.
I don't know if Daniela mentioned what the project is about. So this is we are part of UCL, of a master program called Environmental Design and Engineering, and the student in one of the modules they have to design a house which is passive for a family of 4. And every year, well, for the last many years, I have been trying to do this project in relation to an NGO. And for the last, I think, 4 or 5 years, we have been collaborating with RISE and trying to help the work that they have doing. And for us as a university, it's great that actually our students, they're all professional architects, engineers, and other disciplines. They can kind of contribute and work in a project that is in some way could generate an impact in Lesotho. So yeah, what we're gonna do now, we're gonna start with the projects. We're gonna have 3 presentations, 10 minutes each, more or less. And what we're gonna do, we're gonna have probably 5 minutes questions from you guys to the students as the students finish. Is that okay? Good. So group 7, if you can start with your presentation, if you can share your screen.
Yeah.
And then we go with that. Thank you.
Shall we introduce ourselves like one by one first, or?
Yes, I mean, really briefly, please.
Okay, good afternoon, everyone. We are group 7, which we are the first. My name is Tanya Torn, and I'm an architect from Thailand. And also my colleagues, who are they?
Hi everyone. Okay. Hi everyone. I'm Phoebe. My background is from architectural environment engineering, and I'm from Indonesia.
Hi all, I'm Agatha. I have a background in engineering and science in sustainable innovation, and I'm from Romania.
Hi everyone, my name is Dafa. I have a background in civil engineering and I'm from Indonesia.
Okay, so let's begin. Our group would like to present our projects under the name Passive Solar House in Maseru. This project explores how passive design strategies can improve thermal comfort and climate resilience for a family house in Maseru, Lesotho. To explain our process, the overall workflow is shown in the flowcharts on the right. We began with initial research, including sites and climate analysis, local context study, and shoebox simulations to understand how different design variables affect thermal performance. We then develop a baseline model in IES and refine the design through several iterations based on environmental performance. Finally, the selected design was tested under future climate conditions to evaluate its long-term resilience. I will now start with the research stage of the project. First, we study the sites and climate conditions. Maseru is in the southern hemisphere, where the sun is mainly to the north, while east and west facades receive lower angle sunlight. The south facades receives the least direct solar heat. The city is also located at a high altitude and surrounded by mountains, which affects wind movement. The prevailing wind mainly comes from the northeast, influencing the placements of the rooms and buffer spaces. We also define seasonal comfort thresholds using operated temperature ranges. This threshold were later used to evaluate the simulation's results and judge whether the design could maintain acceptable indoor comfort. And in addition, we tested key design variables through shoebox analysis. This helped us understand how orientation, thermal mass, glazing ratio, and shading could be used as design tool. Next, we analyze the household program based on the environmental needs and occupants patterns. From this, we develop our main concept, which is spatial centralization, where the living area becomes the thermal and social core of the house. This central space improves connectivity, reduces unnecessary circulation, and creates a protected environment for family activities. The surrounding buffer zones help reduce wind exposure, control solar heat gain, and retain internal heat within the house. So based on this research, we then develop our architectural strategy. The living area was placed at the center as the main thermal and social core. Bedrooms were positioned on the west side to retain heat from nighttime use, while the office and all-day use spaces were arranged to reduce exposure to the northeast wind. Meanwhile, spaces requiring less solar control were placed towards the south. And this layout became our baseline design, combining both program requirements that we studied before and environmental logic. And in terms of architectural language, the design became with a central core and side buffer spaces. During the development, front and back buffer zones were added after simulations show overheating from the north facade. The form was then refined to reduce thermal bridging and improve heat retention. Some buffer spaces were vertically extended to increase thermal storage capacity. And finally, the roof design was adjusted to respond to Maseru heavy rainfall and seasonal climate conditions.
For our environmental strategy, we mainly based it on the shoebox simulations that we have run initially, as well as all the design iterations we've been going through with multiple simulations that will be detailed further, thus reaching the 4 main categories of focus, looking at underheating reduction during the cold season of Lesotho, so reducing the cold periods inside the dwelling. Our approach against the elements met in Lesotho of wind and flooding, our overheating reduction during the warm periods and the warm season, so reducing very high temperatures inside the dwelling. And finally, our carbon strategy, looking at our embodied carbon and how we selected our materials, as well as our operational carbon and how the dwelling was being used.
We cannot hear you, Agatha. Or it's just me?
No, we're not hearing you.
Heating reduction, so for improving the temperature inside during cold season, solar gains by the use of increasing me. I will reconnect. 1 second.
No, now it seems that it's working.
Now it's fine. Okay. How much was lost? Have you heard the previous slide?
Can you start over again on this slide?
Yes. Okay, over on this slide. Let me know if it happens again. So for our underheating reduction approach, we worked with a bioclimatic design, looking at using direct solar gains via the use of windows, mainly looking in the picture on the left. You can see the western and eastern facade. So on the western facade, it's the kids' bedroom using direct solar gains, heating the room during the day and releasing the at night when it's being used. Right. Is taking in the morning light, and on the picture on the right, you can see the right of the picture on the northern facade. Trumpy wall function using a very large window, allowing solar radiation through. Heat are made out of being heated during the day, and the heat is the main space to be warm enough. Facade on the southern facade, we use a low amount of windows, almost minimal, in order to limit energy losses as well as cold periods. For our wind and flooding approach, as my colleague said earlier, we work with the organization of the space, so the less prioritized rooms are placed towards the wind direction, where for the flooding, we have raised our foundation about 0.5 meters with by using sandstone, thus allowing the rooms to be protected from flooding dangers. For the overheating reduction, we created a space that was very airtight, used a lot of thermal mass and insulation. So we encountered issues during the warm period with rising temperatures, also due to the use of a lot of windows. Thus, we needed to have ventilation. The way we did that was adding vent holes in key spaces such as the rooms and kitchens, as well as adding window sills that are being able to be closed and open, which you can see in the pictures below, mainly being used by occupants based on their comfort, opening them at night for night purging, allowing cold air to enter the space and cool the place, and during the day, allowing the warm air to exit. Finally, for our carbon strategy, as you can see on the graph of on the left, our overall emissions went down from the baseline design to the final one. In light gray, you can see a small increase in the embodied carbon. This is due to the use of a lot of windows, which we needed for the direct solar gains in order to warm up the space during the winter. However, because of the improvement of the overall house, the operational and overall carbon went down. What was really important to us for both parts of the design, baseline and final, was to use materials that were easily available on site. So in the initial design, we applied brick walls, single glazed windows, concrete block for the foundation, as well as a steel roof. And the additions that you can see on the table, as well as the pictures, is the change from brick to compressed earth block, mainly made out of adobe, as well as adding the shipwool insulation, both in the envelope and the roof, to improve the insulation of the house, which is also a resource that from our research can be easily found in Lesotho.
And next, we test the design performances. From the architectural and environmental strategies, we developed 3 main designs. Each one was tested for different facade materials, U-values, and compositions. Iteration 1 focuses on heating from solar gain through glazing in winter and solar shading from the roof extrusions. Results are evaluated by the percentage of hours within operative temperatures based on seasonal thermal comfort. We analyze per room for each season as the temperature range changes, so the thermal comfort range change. But only the annual data for the whole dwelling is shown here for clarity. The results are good overall, but fall short of the 90% comfort hours target that we set up because we have elderly and children inside the house, which have more thermal sensitivity. Reflecting from the iteration 1, iteration 2 improved the main living spaces by increasing the living room height and adding windows at the top to boost heat transfer, resulting in up to 10% rise in annual thermal comfort. However, many corners in the design cause thermal bridging, reducing comfort in winter and autumn. To combat this, we reduced the corners for iteration 3, making the design more compact while maintaining the height difference between living room and other zones for more solar gain in winter while protecting the living room from overheating. We also added Trombi wall to combat overheating and tried out several natural ventilation strategies by adjusting opening schedules, adding windows and fan holes as shown on the second figure here. The final options with the Trombi wall, natural ventilation, and U-value adjustment gave a 55% thermal comfort percentage annually due to the restriction from the low cost and local materials. The main living areas, such as the living room and bathroom, generally have higher comfort percentages compared to other rooms, especially in summer and spring. Although most rooms don't meet the 90% comfort, temperatures are generally near the comfort range. So if the temperature range were lowered by 5 degrees Celsius in winter, all rooms can meet the 90% requirement. Other adaptive measures, such as wearing thicker or thinner clothes, could also help increase comfort. Both bathrooms meet the CTM59 criteria for overheating, as from May to September, the operative temperature did not exceed the maximum acceptable temperature by 1 degree Celsius for more than 3% of occupied hours, and the bathroom operative temperature never exceeded 26 degrees Celsius between 10 p.m. to 7 a.m. for more than 32 hours. However, the living room, dining room, and workspace did not fulfill the first criteria, raising the need for more ventilation strategies to combat overheating.
So, in this section, we tested the passive house under 2 distinct scenarios: Lesotho's own projected climate in 2050 and the extreme heat of Niamey in Niger. The question we asked was simple: what happens when you take this design out of its comfort zone? What we found reveals a fundamental limitations of purely passive design. Under 2050 climate projections, featuring hotter summers and warmer winters, the design performed poorly. The house rental ventilation was calibrated for today's temperature threshold. In a warmer future, that calibration breaks down. Thermal comfort in the living room drops from 68% in summer to just 23% under the 2050 scenarios. It means the house is uncomfortable for more than 3/4 of the occupied summertime. We then applied adaptive measures. Window openings were shifted to mornings and nights to avoid peak heat. Local trees were planted to provide solar shading and block direct heat gain. It sounds promising, but is limited by seasonal variation and slow establishment. These interventions help. Comfort recovered to 50% of occupied time, but that still means that half the time the houses fail to meet thermal comfort criteria. The hard limit is the outdoor temperature itself, and passive strategies alone cannot overcome that. Also, we should have broaden the adaptation strategies beyond just landscape and trees, such as changing ventilation schedules and shading devices. The Naomi scenarios exposes a more fundamental problem, which is a design mismatch. Maseru's passive house was built to retain heat through cold winters. Naomi's climate demand the opposite, dissipating heat to stay cool. These are directly opposing design goals. Predictably, the building suffered extremely poor thermal comfort year-round from the outset. We pushed hard to adapt it. The building was rotated to align with Naomi's wind and sun path. The facade was painted white to reflect solar gain. Ventilation schedules were altered. External fans were added, and local trees were planted for shading. The result was that the thermal comfort improved by just 2%. The thick walls and heavy materials stopped the building from getting cold, but in Naomi, that's the last thing that you want. The conclusion is unavoidable. So active mechanical cooling and PV panels are not optional in a climate like this. It is essential.
So in overall, this project shows that passive solar design in Maseru requires a careful balance between winter heat retentions and summer heat rejection. Although the final design improved comfort, daylight, and indoor quality, and also embodied carbon compared with the baseline, it still could not meet the thermal comfort target. This highlights the limitations of passive strategies under changing and extreme climates, where additional adaptations or cooling may be required. Thank you.
Thank you very much, guys, Group 7. So I want to clarify for people in RISE and Martin, is that the student needs to look also at not just to design a house today, but actually look at how the house is going to perform in the future. So this is what it was, this climate analysis. But also, Dafa was mentioning an EMA, because part of the exercise is to see how the house will perform in a completely different climate, which is extremely hot, and trying to understand how you can adapt that particular building. But the main message here is how we can design buildings that actually belongs to a particular location only. Because one of the big issues that many architects do around the world is we just copy and paste whatever we see in other climates, and we come and build it in where we live. And that is a big mistake. Anyway, so I don't know if Daniela or the team in RISE or Martina has any questions for this group.
Yes, so there's several of our guys, and thank you guys, well done for that great presentation. I've got a few comments and questions, but anyone else first want to kick off? I know we've got Mojalefa, Palesa, and Cole.
Martina, you have your hand up?
Okay, go ahead. Sorry, Martin.
No, don't be sorry, please. No, I'm happy to wait in turn, or I've got some some questions, but first of all, just to say thank you. What a brilliant, fascinating presentation, and well done to the group 7. So my own background actually is as a climate expert. That is really my career anchor. Being an ambassador is a bit of an outlier for me, so just forget that. So I'm sitting in Maseru at the moment. My birthday gift from my parents-in-law is a heat seater, a seat heater. And I've got the heater on because this building does not retain heat. And this is a modern building built in 2019. It is built for the summer. It is very cold in early winter. So we're coming into not even midwinter yet. So just a few data points for you to work with there. But look, I'm really, you've clearly really carefully considered, the heat retention and the thermal considerations. I really liked, seeing those heat scenarios into the future, and well done for factoring those in. The question I have for you is actually about rainfall variability. We have had 2 quite extraordinary years, but they are not extraordinary because that is the world that we live in. So 2024, a year of drought here. I'm sure Daniela can tell you more about that. This year, we've had twice the annual rainfall, and that extended all the way from September to May. The traditional rainy season here is only from December to about March. So we're seeing this much longer rainy season and very high intensity rainfall. So when the rain comes, they're quite destructive events. They're quite dramatic. So I wondered if you'd thought about variability of rainfall. I know that you've thought about flooding, but how are you going to move water away from the building? How are you going to create shelter for the residents? So, for example, for outdoor spaces, it's warm, but sometimes it rains. So you want to be outside, but under shelter. So that was my main question. The second question I have is, again, great that you've thought about local availability of materials. I love the sheep wool and, of course, the compressed earth block. How are you going to overcome cultural barriers? This country, people here are not comfortable with building with insulation. So how are you going to introduce and overcome those cultural behavioral barriers? That's it from me. Thank you. Well done again.
Thank you very much, Martina. Anyone wants to answer? Who wants to jump?
In terms of the rainfall, we actually considered having trees and stuff as a shading from like the heavy rainfall. And then we also considered having the roof being in that angle, not to put too much water into one area. So like all the waters can all go down. And then in terms of like having an area, a shaded area, we were thinking about it from the Trombi wall. We have like actually a terrace over there. So the windows from like, as you can see from that picture, like you can actually open that and then people can sit on that area. So they can enjoy, like have a sensation of being outside without actually being outside.
And just to add on another, I don't know if there was another question, but just related to this, just really think the importance of having overhanging roofs to protect the SEB walls, because if they get a lot of direct rain, it will lead to, it looks like you don't have a rendering on there, that it's bare blocks. So you will need overhang because they will, deteriorate with a lot of rainfall and directly onto them, and also thinking about rainwater harvesting as well, because shortage of water and access to water is something to consider. So I don't know if there were any other points that you wanted to address that Martine brought up, anyone from Group 7 before. I think Cole has his hands up as well, but did you want to address some of the other points that Martine brought up?
I think just for the material addition of insulation, it's definitely a sensitive point that convincing people, because I assume it's also the constructions could be more simplified. So adding a lot of insulation is maybe not as common. I don't think we went as far as thinking how to push people to go on this route, but I guess just starting from the simplest point of like the thermal analysis that we did lead and showing how much of an improvement it can be, hopefully without a very, very large cost, if that could be possible.
Great, thank you. Yes, and sheep's wool did turn out to be quite a costly form of insulation. Also, there's not enough of it because they can sell even the lower grades into the textile industry for quite a lot. So probably other forms of insulation such as cavity walls and cheaper forms of insulation, even using grasses as panels might be lower cost options. And yeah, numbers talk. So doing how much will it save in your bill? There's actually the first hemp house in Lesotho. The hemp blocks had to be imported from Cape Town. But they've got now they're about to enter their third winter. And there's a case study of how much less gas they have to buy to heat the house compared to what it was before. So cost savings is a very effective way of persuading people. Cole, your hand went down. Did you want to ask your question or comment?
Hi, thanks, Daniela. I think most of you, Martine especially, had hit a lot of the points I was going to say. I'd like to mention that I really do appreciate the extents in which you went down to your research, Team 7. I think from what I know, it was pretty close to accurate. And I appreciate the fact that they thought about not just how the space will be affected within the temperatures of today, but in future going forward. I just want if it is, I would say, something to consider. Culturally, they a certain extent to which they believe that we should have a form of heat produced from the inside. I don't know about that's because of a lack of the insulation because of the material, but there is a sense that culturally the Basotho people or people from Lesotho enjoy having that exchange, having the same situation where you'd have that interaction within a dinner table. It will be done around a sort of heat. That'll be a fire, and more locally or more updatedly, it will be like around a paraffin heater. So I was saying this to ask if maybe that's something that you might consider or maybe would want to consider going forward. I know we spoke a lot about retention of heat, but in the same way how I assume in more modern countries ins you have insulated floors or other floors that emit heat. Would it be something that you'd consider to maybe have a fireplace in a certain direction or have something that produces that heat? Thanks. And thanks very much. Very well done work, Group 7.
Anyone from Group 7 wants to comment on what Cole was saying?
Yeah. We did consider that point really much when we were arranging the functions when we working on the layout of the building. We study deep into like indigenous background, people, culture and stuff. So we discover like how the social spaces that form up, like the common space, the dining areas and stuff like that. So that is also the inspirations where we got our centralization, like the way we organize the functions as well. And maybe to push that further, maybe like the kitchen area, which is connected to like the core space. I think this is maybe like to develop it's further maybe on that place. Yeah.
Okay, can we move on? Because I mean, I just checked the time and we have taken too much time here. So thank you very much, Group 7. Can we move to Group 13 if that's possible, please? I'm really sorry about the time. So can I ask you, because I mean, Group 7 took quite a lot of time, if you can try to do it in 10 minutes, that
Yeah,
would be great, please.
ours is within 10 minutes. So
Wonderful. Thank you very much. I'm really sorry. I should have managed that.
it's okay.
Super. If you can share your screen, Jonathan, please.
Yeah. 1 second. I need to allow access. Can you see my screen yet? Or no?
No.
Not yet.
There we
It's
go.
coming now.
Yes.
There we go.
Okay, awesome. All right, how does that look? Does that look
Yeah,
good?
perfect.
Okay, perfect. So yeah, hi, we're Group 13. Welcome to our presentation exploring the design of a sustainable dwelling for Lesotho. I'm Jonathan. I'm an electrical engineer, and I'm from London in the UK.
I'm Yanni. I have a background in architecture and I'm from Spain and Scotland.
And I'm Majid. I'm from Saudi Arabia and I'm an architectural engineer.
Okay, nice. So unfortunately, we had one other person in our group, Tom, but he couldn't join us today. So yeah, we're a 4-man team. And yeah, so starting off for some background to our design process. So our allocator location was Maseru. And before conducting any building design or modeling, we analyzed Maseru's climate alongside choosing a site for our dwelling. So as you can see on the left figure, we chose a site located in the northwestern part of Maseru, with the middle figure demonstrating that this was a largely residential area with good access to other services in the near vicinity, alongside good transport connections. So our climatic analysis covered aspects such as the local temperatures, humidity, sun path and angles, and wind directions. The graph on the right presents one of those outputs from the temperature analysis, which demonstrated the significant seasonal variation in temperatures, with the average monthly external temperatures being outside the thermal comfort zone we defined using the globally recognized ASHRAE 55 adaptive thermal comfort method. Alongside this, substantial diurnal variation in temperatures, as you mentioned in your introduction earlier, were found from the analysis, highlighting the need for the dwelling to be able to provide both heating and cooling to maintain occupant comfort. The outputs of these analyses were then used to inform the environmental strategies and design focuses for our next stages of design. So we also did shoebox modeling, and this was the next step of our design process. So this involved using a basic building structure to isolate and model the effect of different building characteristics to optimize thermal comfort in an attempt to find the most ideal combination. So we ran over 100 simulations for the shoebox modeling, with the figure presenting the variance we modeled for each category, alongside the optimal variance in blue. We found a combination of a north orientation, a sandstone sheep's wool and hempcrete wall construction, a sheep's wool insulated thatch roof, a single glazed window with a high G value, a floor construction combining sheep's wool and hempcrete, windows on all sides of the dwelling at a 40% window to wall ratio with vertical shading, and a trombor on the east facade as the most optimal combination. The findings of this shoebox modeling were then used to inform the detailed building design, providing a basis for further iteration and development.
The design process was highly iterative, with early stages focused primarily on architectural design. From design 2 onwards, thermal performance became more of a consideration, with design 3 introducing features like the trombor and sunroom to address underheating in the master and kids' bedroom. Later stages also prioritize embodied carbon, incorporating local materials in designs 4 and 5. And initial sketches help to define zoning based on sun path and prevailing winds, helping to differentiate private spaces with communal kids spaces. And the dwelling was orientated along the north-south axis in line with the earlier shoebox modeling, and also supported by sun and wind analysis. So this diagram illustrates the final design through an exploded axonometric, revealing both the spatial organization and internal environmental strategies. So various passive strategies were implemented alongside comprehensive thermal analysis, and each play a significant role, from on-site PV generation, thermal comfort measures, and ventilation requirements. The layout also utilizes thermal zoning, where spaces are grouped based off differing comfort criteria. We have a thermal corridor which acts like a buffer, mirroring a double skin facade, which helps to reduce heat loss and regulate internal temperatures. The ground floor plan portrays the zoning a bit more clearly, as well as the thermal corridor and the entryway. The zoning, as mentioned earlier, follows the sun path of Lesotho, with the main kids area positioned to the northeast to capture the morning and daytime sunlight, supported once again by that trumb wall for passive heating. And the first floor follows a similar strategies where bedrooms are located along the north side to maximize that solar gain, with the sunroom also acting like the trumb wall. The overhang was designed to enable the lower angled winter sun to enter and enable that passive heating, while also shading from the high angled summer sun. The prevailing wind direction was also considered to enable airflow within the house and is shown on the sketches of this page. Additionally, an important component of the ventilation strategy is the stack ventilation capability, using gear-controlled windows at a high level to enable that hot air to be replaced. That's shown in those green circles. Alongside this, the open plan and double height space in the corridor enables that greater summer natural ventilation and airflow within the house. And a sliding partition also allows the kids' play area to be isolated in the winter to reduce heat loss. We analyzed the summer and winter solstices to confirm the shading design elements are effective as intended via the shadow placements. And we evaluated the daylight performance using the SIBC Guide A SDA metric of 300 lux using Grasshopper, and as shown in the table on the next page. All spaces exceeded the 50% threshold, except for the bathrooms, which follow different daylight requirements. This page illustrates the north and south elevations and a view from the balcony. The north elevation portrays, you can see the sunroom and the trombe wall, as well as the sandstone cladding and the incorporated PV panels on the roof. And here are some more views. So the left being the rear view, again showing the environmental strategies of the trombe wall and the sunroom, the balcony, sliding door, and the right being the interior view of the kids' play area, showing an open plan design with the easy access to the garden via sliding door.
So, alongside the detailed architectural design, we were constantly evaluating the thermal comfort performance of the dwelling's 5 main occupied rooms against that ASHRAE 55 base thermal comfort ranges we highlighted earlier. As mentioned, this also informed changes in the iterative development of the final dwelling's design and environmental strategy use. The figures on this slide present the thermal comfort outcomes of the final building design running in passive operation. The dwelling demonstrates very strong thermal comfort performance, and in winter, every room achieved temperatures within the thermal comfort range at least 80% of the time. While the summer performance is even stronger, with every room achieving over 92% of time within the thermal comfort range. These outcomes clearly highlight the merit of the dwelling's design to maximize the potential of the passive and environmental strategies, resulting in the very strong thermal comfort you can see here. Nonetheless, despite the strong thermal comfort performance under passive operation, active systems would still be required to achieve 100% of time within the thermal comfort bands. The figure on the left shows the annual heating and cooling load profile versus the annual PV generation load profile. We considered a standard size PV generation package available from Viessmann, a global PV manufacturer, for this analysis. As clearly shown in the figure, the system load profile is highly variable across the year, whereas the PV generation profile is comparatively constant. Overall, the total annual PV generation is actually greater than the annual active system load, but following further analysis, we found that the timing of the PV generation typically does not coincide with the peak active system load. Hence, if only a direct connection were to be used, then only 28% of the active system load could be met with the PV generation. This would imply that a grid connection would be required, as shown in the table on the right. However, the larger PV generation output than the active system load shows the potential for an on-site energy storage system, such as a battery, to enable the dwelling to be entirely solar powered, hence only requiring a grid connection for backup purposes. And this leads into your point about savings you could make on your energy bill.
Our material selection was driven by 2 principles from the start. Use local materials wherever possible and quantify the impact so design decisions could be justified. on carbon grounds, not just intuition. Embodied carbon was tracked formally from design iteration 3 onward, with iteration 3 being our baseline and iteration 5 being our final design. The figures on this slide show the cradle to gate embodied carbon for iteration 3, 4, and 5, calculated using ICEV3 databases alongside other sources for local materials like hempcrete. As shown, our baseline iteration 3 came in 591 kilograms of carbon dioxide equivalent per square meter. Iteration 4 actually went up to 648 before dropping significantly to 436 in our final iteration. A reduction of around 25.5 tons between iteration 4 and 5 alone. And as you can see on the slide, the table and the graph showcasing the differences between each iteration, and on the right, our final materials selected. There are two key material switches behind these numbers. The first was moving from away from thatch roofs between iteration 3 and 4. Although it has a very low carbon and good local availability, we had to divert from thatched roofs for three practical reasons. First being buildability concerns with the proposed roof pitch, the inability to mount PV panels on it, and concern over fire safety and structural integrity. The second key change was removing concrete between iteration 4 and 5. Concrete has a high embodied carbon and isn't local, so we replaced it with timber joists and hempcrete infill. This single change alone is what made iteration 5 this much lighter than iteration 4. And finally, in the next slide, looking at the cradle to site emissions, our local first approach meant the majority of materials were sourced close to site, Beera and within Maseru itself. Some materials had to be sourced from South Africa, clay tiles, glass, and sheep's wool from Bloemfontein, and hempcrete from Johannesburg. Still, transport carbon only came to 4.5% of the total embodied carbon, well below the typical 10% benchmark. Overall, the final dwelling achieved a cradle-to-site embodied carbon of 457 kilograms of embodied carbon equivalent per square meter, comfortably under the RIBA 2030 residential target of less than 625, demonstrating the merit of our iterative carbon-driven material decisions. And that's our presentation for today. Thank you guys for listening.
Thank you very much, guys. I'm really sorry that we're taking longer, everyone. So do you have any questions for group 13? Thank you, group 13.
Really impressive. I love the way you also took the transportation into consideration as well with that data. Some really useful things, and hopefully one day we'll be manufacturing hempcrete in Lesotho as well. So reduce on that. That's what we're really advocating and lobbying for. I love the design. It looks beautiful and really interesting about the drone ball and all that passive design. My only concern is about affordability because this looks like a really luxurious house. And yeah, I know costing isn't something that you had to take into consideration, but how practical is this? I think we'd need to scale it down and take some of you. I love the flow of the windows and all the things you've got going on with the light and circulation, but how to bring it down to make it affordable, perhaps to look at densification of houses as well. Because as we are getting more and more urbanization, people moving into urban areas, gone are the days of the luxury of having your own plot. We need to have sort of more detached houses are something of the past and something we need to adapt the designs for. But beautiful design, guys. Thank you so much. I don't really have, those were just some comments that I had rather than a question. I don't know if anyone else had any comments or questions.
Martin, Cole? If not, we can go to the next group.
No questions from me. I mean, I love the sunroom idea. I'd love it if you could build this house for me, please. but no, in all seriousness, I mean, I think Daniela's spot on with the affordability that's going through my head. You know, the logistics of buying things over the border and bringing them in to Lesotho is challenging. Very slow customs processes, very cumbersome. And, you know, you can spend hours at the border, you know, even in just a passenger car, let alone in trying to transport significant materials. But no, I mean, it's a very inspiring space that you've created. So thank you for sharing it, and clearly lots of really good work's gone into it. So yeah, no questions from me. Thank you.
Thank you very much. I mean, you have made so many good points, called Martina and Daniela, because I mean, the student, if you think, they have to look at how they can design a house that is passive. But within that, we need to consider climate change, affordability, materials, cultural aspect, like, for example, having a fireplace inside. So there are so many aspects, and make the project super, super complex. And removing all these complexities, still the project became super complex as it has been designed, as you can see, by students. So
I did just have one thought that came into my mind, which was something that you said right at the beginning of the presentation in terms of site selection. I was interested about that. This is more of a comment than a question, but I noted that you chose a particular area of Maseru because of its density and therefore an assumption around services. I'd always question your assumptions. In cities like Maseru, this is true in lots of places around the world, there is very poor urban zoning and very poor urban planning. It's not a big problem here because it's a relatively small city, but it has huge urban sprawl. But actually, in terms of services, in terms of transport connections, there is no public transport here, none. So I just wanted to, in the future, as you factor in, you know, as you think about, site selection, just interrogate your assumptions. And, you know, it's difficult in these environments to get the latest, you know, without being here on the ground in terms of what's happening on urban planning. But zoning here, and Daniela, I'm sure, can fill you in on all the ugly, gory details. But you know, zoning doesn't really exist. So the area that I'm in used to be a residential area. That is no longer the case. And zoning is now, we have been told we're now in a mixed zone. And that means that all sorts of buildings, so a beautiful heritage building across from our plot has just been demolished with no planning permission. And apparently there'll be a 7-story headquarters with 400 car parking spaces. So yeah, just question your assumptions about location. Thanks.
Thank you very much. So can we stay another 15-20 minutes, please? And I promise that we're gonna go. So let's go to group 4, please.
Okay. Hello, everyone. While Heidi shares the screen, I will just begin with the introduction. We are Group 4. My name is Luz Toro. I am an architect from Colombia with experience in vernacular architecture, sustainability, adaptation, and resilience. I work with Negi, Heidi, and Charlotte in this project. Negi and Heidi, can you introduce yourself, please?
You're muted, Heidi.
Can you hear me?
I don't know whether I can share and speak at the same time. I must have touched something. Hold on. Sorry. I'm Heidi. My background is environmental engineering, and I'm from the UK. Can you see my screen?
Yeah, now we can see.
Oh, nice. Okay.
Nagin, can you introduce yourself?
Is she still here? So I know she's...
Can you hear me?
Yes.
Yeah? Okay. Hi. Hello, everyone. My name is Negin. I have an architecture background, and I'm from Iran. Yeah.
Great, thank you. Our project begins in Mokhotlong, where the climate creates a very specific conditions, as mentioned before, so I'm not going to get into the details. And so the question for us was no simple how to design a low carbon house, but how to design a house that can care for people across changing conditions. And this matter because the house is not only for a family, it supports elderly caregivers, and it has a daytime nursery for young children, and that may comfort the life, resilience, social issues are much bigger than just an environmental issue. For RISE, it means that the project has to be affordable, locally appropriate, and robust, and not just efficient in papers. I think we try to make the best with the information that we have. From there, the group tested different passive design strategies, local materials logic, adapted environmental layers that could work together to create a house that performs now, but can also still respond to the future. I will pass it to Heidi.
So our influences. So the first influence we had was the vernacular architecture in Lesotho. So this was all like the thatched roof roundhouses. Another influence was Rice's focus on the Sustainable Development Goals, which are shown on the slides. And then finally, our shoebox model. So a significant challenge we saw was the amount of underheating in our shoebox model. So we investigated multiple different iterations and found that the best way of improving this was to increase the insulation and ventilation. This created a improvement of comfort in the space by about 80%, and that was within the comfort range of 18 degrees to 24 degrees.
Sorry. Yep. In terms of in terms of in terms of architecture concept, the architecture concept was inspired by traditional vernacular architecture, and in traditional homes, spaces are organized around communal living, and we translated this idea into environmental design by creating a rounded front courtyard that acts both a social gathering and a climate buffer zone. So this courtyard works as a transition zone between the exterior and interior, and it provides a greater sense of privacy and safety for the family and children. And at the same time, it acts as a thermal buffer spaces, reducing direct exposure to the strong winds in Mokhotlong's mountain climate. And the main focus of this design is having a home in a simple way. So it was treated not as a this simplicity, it was treated not as a limitation, but as a design principle. We consider adaptive outer skin made of operable timber louvers and shutters surrounded indoor zones. The idea was to design a building that can change its behavior depending on the season. For example, during winter, the shading panels can fully open to maximize passive solar gain and allow sunlight deep into the interior space. But during summer, the same system can close gradually to reduce overheating. And in terms of orientation, it was one of the most important strategies because the site is in the southern hemisphere. So we put windows and glazing in the north side of the design. So some spaces like nursery and living areas, which are occupied most during the daytime, were placed on the north facade to maximize daylight and service spaces and circulation areas were positioned in the south part. The idea in terms of window placement strategies, since the cold winds mainly come from the west, so we intentionally minimize opening on the western facade. Heidi, could you please? Yeah. We put opening on the western facade to reduce heat loss, and we use a more solid thermally resistant wall construction. At the same time, larger openings were positioned mainly in the north facade. And for rainwater harvesting was also integrated into the design as part of the sustainability strategy. Since infrastructure and water access can be limited in that area, collecting and storing rainwater was one of our considerations. So, and skylights were introduced not only for the daylight, but also to improve natural ventilation and solar penetration. Yeah, I think Luz can.
Yeah. So in terms of energy performance, we used IES to model the building. The biggest challenge was, like in the shoebox model, was the underheating throughout the year. So our baseline model had an average underheating value of 17.5% in the comfort range, and then with a few iterations we managed to get it up to an average of like 71.5%. So the 5 iterations, as you can see on the table, so the baseline was like just the shell of the building. So iteration 1, we added the windows. 2, we added upgraded fabric, so incorporating some insulation. 3 was introducing our ventilation strategy, so the cross ventilation through the building. 4 was the introduction of external shutters, and then 5 was actually reducing our comfort range. So initially it was at 18 degrees to 24, but we actually found reducing it to 17 to 24 degrees, which actually reflects more of the current climate characteristics, came up with a better result, and 17 degrees still remains within the CIBSE Guide A compliance, so it's still in the benchmarks, but it's just, it works better for the building.
As for the daylight, was especially important because the house also functions as a nursery. It is not only about reducing light demand, but it supports children's well-being, visual comfort, rhythm, and quality of care. Our deadline strategies came from a broader concept of layering, rather than treating the facade as one fixed boundary. We design it as a sequence of environmental layers, thermal mass, glazing, shade, thresholds, and operable timber louvers. The glazing brings in deadline and winter solar gains, while the louvers filter glare, reduce excess of heat, and allows occupants to adjust the building through the day and across the seasons. This layering also has a cultural role. The louvers extend the idea of protected threshold between inside and outside, supporting privacy, protection, and adaptability. The deadline analysis show a strong performance according to the standards in the main spaces that are occupied during the day, but also created a glare risk in some areas. So the louvers layer allows to keep generous deadline while giving us control over brightness, heat, and comfort.
In terms of embodied carbon, we use the Bath ICE database and LETI benchmarks to calculate the overall embodied carbon. So we chose 4 different options, but we ended up taken forward iteration 4, which was the use of sandstone and wall insulation and then clay tiles for the roof. This was mainly due to the durability of the materials for the climate, but also the total embodied carbon result is well within the LETI benchmark. So yeah, that's why we decided to take that one forward in the design.
For future robustness, we ask a simple question. Does this house only work for Mokhotlong today, or can it still support comfort as the climate change? The first layer of the building envelope in winter, the house use north-facing solar gains insulation and thermal mass to retain heat. But in warmer future conditions, the operable timber louvers become a protected second skin. They reduce direct solar radiation before it reaches the glazing, while still allow the light, air movement, and privacy. So the facade can shift between heat capture and heat protection. The second layer is the courtyard and landscape. Instead of leaving the courtyard as a hard exposed surface, vegetation can reduce heat around the house through shading and evaporative transportation. This helps cool microclimate before air enters to the building, making natural ventilation more effective. The courtyard, therefore, becomes more than a social space. It becomes a thermal buffer. The third layer is a water and flood resilience. Rainwater harvesting helps to reduce water dependency, but the landscape can also be shaped to slope, absorb, and redirect storm water away from the building. Planting permeable ground and drainage age can help manage heavy rainfall in the future, and the site work as a part of the resilience system rather than just a building alone. The final layer is the future adaptability. The courtyard is currently open, as you can see in the design, but in the future, it can be grow, like the wall can grow and it can be redesigned. We thought that while we were doing the design process. So it can become an enclosed shading space with light weight glazing or screens and more like a buffer space between inside and outside. That means that the building leaves space for adaptation over time instead of assuming the first version of the building will be enough forever. And so future robustness here means environmental redundancy. The house can store heat, block the heat, ventilate the heat, cool the surrounding microclimate, manage water, and adapt a courtyard. This makes the proposal more resilient, not only as a building, but as a small domestic landscape that keeps support, care, comfort, dignity under changing conditions in the future. Thank you so much. This is all of the presentation.
Thank you very much, Group 4, for your presentation. So, Daniela, Martin, and anyone that wants to ask questions to this group?
Yeah, I'll go ahead and then I'll hand over to Martin and anyone else. There's 5 or 6 of our fellows on, so please put your hands up. We've got Cole Palessa, Jeff Dintley, and Sabati and Chaka. So I'd love to hear from you. Just go ahead and put your hands up if you've got any questions or comments. I love the way, thank you so much, Group 4. Love the way you took also the rondavel into consideration into the designs of the vernacular. I think the walls did you go for concrete in the end, the material that you chose?
It was a sandstone.
Sandstone for the walls. Okay. I caught that for the floors. Okay, great. Yeah, sandstone is quite costly, but yes, a beautiful design. Really, I think you captured a lot of the the communal sort of aspects of the culture into the design of it, and the aspects, especially Mokhotlong is a very, very cold, mountainous area, so the importance of capturing the sun. The louver timber is a very interesting potential solution. It's been used in metal, actually, in a school that Pedro, one of our co-founders, designed in a sliding sort of panel to create a thermal corridor at the beginning on the outside, which I think the previous group had something similar. But you don't really see them around in of wood. The timber is not that much used in Lesotho. Hardwood is a bit hard to find and on the expensive side, but definitely a very interesting potential solution to the challenging climates of the mountains, and one which we should look into more, and perhaps do a bit of cost analysis of the different types of materials that they could be made from. I'm aware of the time as well, so I'll keep my comments brief, but well done. Thank you so much. And it was really interesting to see the different designs of all the three groups come together. Thank you for all your work.
Thank you, Daniela. You know what? But I want to say that there are 15 projects, and this is 3 that were selected from these 15. So, I mean, probably what I could do, I can send you some pictures of all of them, so you can see how much they vary between the groups.
Yes.
Before we I mean, Martin or any other member of RISE, if you have any questions, can send us an email and we can pass it to the student. That'll be great. Probably what I'm going to do also is I'm going to share with you the projects and the presentations, if that is okay with the students. So if you want to know more about the project, then you can probably direct your comments to them later. Martin or any one of the team before we leave?
Yeah, sure. Thank you, Hector, and thank you to all of you. Thank you for giving me the opportunity, really, to hear from you. I don't have an engineering or architectural background, and I can hear from your presentations, the expertise that you all have. So I'm excited to follow you in the future and see the sorts of things that you create out in the real world. I think, for me, with my climate background, I'm thrilled to see how much consideration you've put into sort of future-proofing your designs. I've only been here in Lesotho for 9 months, and I would describe the weather as pretty wild. It's pretty extreme at times, and we are in the lower elevations of the country, as Daniela said, out in Mokhotlong, really at altitude there, people are really exposed, and so of course that impacts how people live, how people work, how people interact. So I think you've done a lot of thinking about those different scenarios in terms of climatic scenarios, but also I particularly loved in the last presentation, you've thought so carefully about those aspects of living, and I loved in that last design the feeling of movement. So thank you. It's always good to hear from students because it makes you feel optimistic. I have to say that after 9 months here, some aspects of urban planning do not leave me feeling particularly optimistic. And so thank you for giving that back to me. I hope that some of you might come and visit at some stage. Daniela's organisation RISE is doing some really brilliant work here. There's a lot of work to do in terms of overcoming cultural barriers. Even in my team here at the embassy, we've had conversations about insulation, and it's not a subject at all. And so there's a lot of work to be done to raise awareness about different building design standards, materials. So I think there's lots of opportunity here. But thank you very, very much indeed. I have to sign off now, but it's been a real privilege and pleasure. Good luck with the rest of the course. and I'll be following you from afar. And if you ever do find yourself in Lesotho, pop by.
Okay, thank you very much, Martina. Before you go, can we take a picture of everyone, please? If you can turn on your cameras.
Take my
If that is
glasses
okay.
off.
So I want to take one my laptop, but if anyone wants to take one too, please, because I'm not the best for this kind of stuff.
Yeah,
so
Lesotho, Dintle, Palesa, Chakav, you can Sabati.
I don't know if you can do it, Vale, too. Really quickly, take a picture, and then we can go. Great.
And while we all do that, I guess we should all smile. Wanted to, really thank you all for all your time and all your incredible designs. Thank you, Hector, for choosing Rise and Lesotho for this project again. Thank you, Martine, for your time on the call today, and thanks, Valentina, for guiding the students throughout the course as well. And thanks also to the pioneers who are on this call. This is a great opportunity. I see Saba now as well. A great opportunity for our fellows to learn about how you guys go through your research and do your presentations. If we had more time, there would be more time to exchange. So perhaps next one, Hector will think about how to do this and get more of our pioneers involved in the reiterative process. We normally organize an annual workshop that's 2 weeks that you actually get to work on a practical project in Lesotho. This year we decided to put on hold with all the war and Middle East sort of flights being affected. We're not going to have one this year, but please do subscribe to our newsletter and our YouTube channel. We do also have monthly webinars, and it would be great to get you involved and to keep getting your input in the work that we're doing. So please remain in contact with us, and really thank you for all your input, your ideas, and your hard work, and wish you all the best with the rest of your studies and your course. And thanks, Hector, for the continued collaboration. And if you could share the folder with the presentations, I will also share them with our team, and we'll keep you posted on the conversations that we have ongoing on bringing this to a reality.
Good. Thank you very much. You two have said everything. So thank you very much, guys, for having the time to see the work that our students are doing, and well done. I mean, our students. So thank you very much. Good. So now we can leave you. You can go. Thank you very much, everyone. And
Bye.
Nice to meet you, Martine. Nice to see you, Daniela, and everyone in Rice. Vale. Bye bye, guys. Thank you.